lot of information in a short time. I have 12 minutes. My case is the following. I argue that a strategy for exploring for alien artifacts near Earth is a credible alternative approach relative to the existing listening to stars strategy of SETI, exemplified by the Breakthrough Listen program. The reason to do that is that I maintain that it's at least as probable to be successful in the near term as the listening program, which has been underway more off and on for 60 years and has eaten all the low-hanging fruit. The point here is that alien artifacts are, in fact, the ultimate technosignatures. They prove immediately that life and civilization exists elsewhere, and they cannot be ambiguous in the same way that a radio signal can be. Essentially, what I'm talking about is a plan B for SETI, which the acronym for this is called SETA, S-E-T-A, Search for Extraterrestrial Artifacts. It's been proposed for 40 years now by a number of people, but I found a way to quantify and compare this strategy against the traditional listening to stars strategy. It shows that it's credible to look for artifacts now because of changes that have occurred, such as in our own space technologies and in the fact that we have found nothing in 60 years. This is argued in a number of papers that I published in the last year or so. There are three. The key one is a Drake equation for alien artifacts, which quantifies this argument. The other two point out that there are nearby objects closer than anything except the moon, which have not been explored in any serious way by mankind, and were only discovered in the last 10 to 15 years, the so-called co-orbitals. And the third paper points out that we've had stars come very near the solar system over geological timescales. And therefore, sending probes here has been easy for some stars in the relatively recent past. This argument was made first by Bracewell in this beautiful book of his, and in which he pointed out that the alien civilizations would be interested in Earth because it has an ecology. And I'm going to conclude that moon and the Earth, our moon, the Earth Trojans, and the co-orbitals are likely places that they would be located for reasons that provide materials and concealment and a stable location. It's relatively unknown to most people that oxygen has been in our atmosphere for billions of years, and that therefore the atmosphere is out of chemical equilibrium. This was pointed out by Lovelace 60 years ago. And we have the only out of equilibrium atmosphere in the solar system because of life. The existence of an oxidizing element, oxygen, persistently indicates that there's life here. And it's because of plants, basically, and animals interacting with the atmosphere, which has been true for a very long time. We've had substantial levels for 65 million years, 650 million years, 2/3 of a billion. And in fact, the oxygen has been present at some level for about 2 billion years. So it's not, we don't tend to think of it this way, but we're revolving around the galaxy every 220 million years in a torus, and therefore stars are streaming past us and getting near us on a continuing basis. Very few astronomers even know that a solstice star came 70,000 years ago to within 8/10 of a light year of the solar system, and therefore disturbed the Oort cloud and has passed on. It's a high velocity star. It's actually a binary. And in fact, other stars will pass by in the future, shown in this diagram. The history of this has recently been, here's another way to look at that. Alpha Centauri will get down to 3 light years. If you look at millions of stars, You find, if in the horizontal axis, millions of years, and the distance they came within in parsecs vertically. So you can see there have been a number of stars that have come in the last millions of years, pretty close to the solar system. And one thing SETI could do is start listening to the stars that came past recently and see if they're broadcasting toward us, because they might have, for example, such a star might have noticed that there are these primates in Africa who were doing pretty well with tools, and they might be curious to know what is going on now and send the occasional radio message. So those are likely targets for listening. The most likely place to look is the moon. The LRO photographs, so lunar reconnaissance orbiter photographs, tell us that we can see details down to a foot now over the whole surface. There are 2 million plus photographs by LRO. Very, very few of them have been looked at. And so the first thing we would do to look for artifacts is look for photographs of artifacts on the moon. We can resolve down to about a foot. And we know that artifacts we've left there, NASA maintains that the Apollo artifacts will be there for 1 to 10 million years, depending upon size. They would be gradually broken down by micrometeorites. So that's a long time scale for artifacts to stay. The next most likely targets would be in the Lagrange points of the Earth, which you can see L4 and L5, and we have found one asteroid, we think it's an asteroid, one Earth Trojan object at L4 about 10 years ago, and we haven't found any others. They're rather hard to observe. The nearest, the single Earth Trojan we found, called 2010 TK7, discovered 11 years ago, orbits above and below the plane and near and back and forth to Earth, but is an excellent vantage point from which to see events on Earth over a long, long time scale, and is stable, and a probe put there 10 million years ago would still be there. That's the point, you see. We're talking about ET archaeology. We're talking about looking into the deep past, whereas the existing listening to stars strategy asked us to simply listen in the present, a very short time interval, as long as the message we might receive. Here are the facts about the Earth Trojan, but I don't have time to go into it. The third class of objects are the 3 types of co-orbitals, which are the closest objects to Earth beyond the moon. They're not actually bound as moon, but they sort of seem like the moon because they stay near us all the time. They're simply orbiting the sun at the same rate, at the same distance on average. But their orbits are typically more elliptical, and therefore they seem to revolve about us. For example, like the Horseshoe Orbit, which comes once a year to one side of the Earth or the other, and then goes back around the other way, and then appears on the other side of the Earth. A quasi-satellite is one that appears to orbit the Earth, but is not actually bound within the whole sphere like the moon is. Here's the nearest of them, the 2016 HO3, orbiting the Earth at a distance of about 5 million miles on average. The Chinese are sending a probe to HO3 in 4 years. We know nothing about it, really. There are no images, no spectra, and all we know is its albedo, because the people who studied the co-orbitals are orbital dynamicists, said that now they know what they need to know. These are the parameters of it. It's fairly small, about 100 meters, gets to within 5 million kilometers, not miles, and was discovered only 5 years ago. What we could do in the near term is to use planetary radars to image such a co-orbital and the other co-orbitals. And here's an image of a 1 kilometer asteroid taken only within the last year at a distance of 5 million miles. So you can begin to resolve and look for and see if there's anything interesting going on there. I have produced in the Drake equation paper a ratio, a so-called, let's say, a success ratio between looking for lurkers, as I call them lurkers because they won't necessarily want to be seen, versus listening to the stars. If you take a ratio of the two Drake equations, almost all the factors cancel out because they all deal with the probability of a civilization existing. what you're left with is a ratio of the fraction of civilizations which would make probes divided by the fraction that would radiate, which I would argue is typically on the order of 1 to a 10th. Right now, for us, it's 0 because we don't know how to build probes that go fast, but to go and stay at a star. But we will within a century or two. The second factor is the ratio of the time you could observe the Lurker, which could be geological timescales, divided by the time of the message you receive, which we know would be only as long as we listen, which isn't really very long at all, measured in hours. So I have much more. I can go into detail about what the analysis shows, but qualitatively it says the two strategies are competitive numerically, quantitatively, and the argument is presented at length in that paper. And the Moon and the Earth Trojans are the most likely places to look. What do we get if we follow what I'm advocating? We develop an AI for looking at the moon. That's actually already been done. We have an AI that can inspect the LRO photographs. It just simply needs funding. So there's a cheap entry point to this strategy. All you have to do is start looking at the photographs you already have. We can conduct passive SETI observations of the co-orbitals, which we already have the planetary radar for. We can use planetary radar and also to send pulses to it and listen for any response from it, which I would think would be unlikely. I think the most likely artifact you would find would be ancient. So we're doing, as I said, ET archaeology. And of course, then we can send probes. The Chinese already are sending a probe to the co-orbital, and just a few months ago sent a probe to the Lagrange point, L4, not to the Earth Trojan that we know of, but to look for additional Earth Trojans. They have not reported their results. And that's the Chinese mission, which will, now they're going to launch in 24 to 2016 HO3. What's the cost? What's the benefit? The cost is it takes time, the use of facilities, manpower, but there's a cheap entry point that costs very little, and that is start looking at existing photos and start using get on this schedule for planetary radars. What do we gain? New astronomy. We know nothing of these objects. We have no image of these objects, the co-orbitals and the Earth Trojan. And anything we learn is news. We know practically nothing about them. But the key thing is this: it's an active, fresh front in SETI research. It's not just passive listening. It requires different skills and a different exploratory point of view, and would change the landscape of what SETI has been for 60 years. I can explain this. Here's the rate at which stars pass within a distance r of the sun. That's in the third paper. There's an additional factor in the ratio of Drake equations, and that's that the distance to them. If you include that factor, the volume over which a Lurker would be able to come because of the speed of the probe, and the distance over which a beacon would broadcast, which is determined by the cost of building the beacon and the cost of operating it. The conclusions you come to, and in the paper on the Drake equation, I present several scenarios where you make differing assumptions and calculate what that ratio would be quantitatively. And the conclusions are briefly as follows. If you're an early spacefaring civilization, as we are, you build beacons. You build beacons because we don't know how to send probes over interstellar distances, not yet. But that's a transitory phase and will go away within a century or so. So in that case, you go for radiators. You'd also, but if on the other hand, if you're a superior civilization with fast interstellar travel, and being able to rendezvous and orbit in a distant starship system. Then you would send Lurkers. The quantitative argument goes for Lurkers because you'd get a whole lot more you'd get information back, which you do not get from a beacon. You would, and therefore it becomes more valuable. And the economic arguments are contained, by the way, within these scenarios. The other thing is, if cost doesn't matter, you'd surely send Lurkers because of the data return is so much greater. On the other hand, I think that putting a Lurker in co-orbital locations is less likely, especially if it has a short lifetime. The lifetime of co-orbitals runs between 1 and 10 million years. And so putting it there means you lose it within 1 to 10 million years in any case. But the stability is something you would have to evaluate before you land there. So I think the most likely thing is that you would find alien artifacts on the moon, which has its own problems. Putting a probe on the moon to watch the Earth over the long term means you have to put up with half the time you're in the dark, and you have to deal with big temperature swings and a variety of micrometeorites coming in at a couple of miles per second.
Jim, I just want to make sure we come to we want to get some time for questions. You got about 2 minutes left.
I'm ready for questions. You've heard my proposition. That is, we have a strategy we haven't followed, which is at least competitive with the one we are following. Thank you.
Hey, Jim, thank you. Have you thought about using a crowdsourced strategy for the image search, similar to something like SETI at home?
Oh, a credible strategy for the energy search. Well, Daniel Engerhausen in physics at Zurich and his group have already produced the AI and tested it against LRO photographs. So that protocol is in place. It needs funding to actually look at the millions of photographs we actually have. So that's in the bag. And so I think it's just the obvious entry point for a SETA strategy.
Thank you. And we've got about 1.5 minutes left. But what are your thoughts on the UAP, or Unidentified Aerial Phenomena Task Force, the UAP Task Force, or the Galileo project in relation to your ideas on SETA?
Galileo is consistent with what I'm talking about. UFOs, I've paid attention to them for a long time. I don't think much of it.
There we go. And that gives enough time for another question. Are there any artifacts which would be the most exciting to find? Specifically, do you have ideas whether they could be scientific probes or even art or anything in particular?
The thing you'd like to find would be a Rosetta Stone. What you'd like to find is something with information on it, and you'd like to find something big so it's easy to find.
Okay, and final question. How many of the close approach stars, when you were showing us earlier, have been listened to by SETI?
Well, I don't know, frankly. I doubt that they have. I think that they should. They should pay attention to stars that have come nearby within the last, say, 10 million years and might be interested in us, might have sent a probe already and be wondering whatever happened to those apes in Africa. So I'd say they really should do that. The rate is basically this. A new star comes within 10 light years of Earth every 5,000 years.
Wonderful. Thank you, Jim.
Jim, that was great. Thanks very much. We appreciate it.